Today we're going to talk about what might just be the most important algorithm in history. Seriously, it's so old and so crucial that it's earned this amazing nickname, the granddaddy of all algorithms. And get this, it's a piece of math that you, yes you, probably use every single day without even knowing it.
Okay, so when I say Euclid, what comes to mind? For a lot of us, it's that amazing new space telescope, right? The one making an avalanche of discoveries. And yeah, that's super cool, but we're not talking about the telescope. We're winding the clock way back. To the ancient Greek mathematician, the telescope was named for.
So to get a handle on his most famous idea, we don't need to break out the heavy calculus or anything. Nope. All we need is a simple, kind of visual puzzle. Just imagine for a second, you've got a floor, and you need to tile it.
Now, at the very heart of this puzzle is this thing called the greatest common divisor, or, GCD for short. It sounds complicated, but it's not. All it means is finding the biggest number that can divide two other numbers perfectly without leaving any remainder. So for our floor, it's just this. What's the biggest possible square tile we can use to cover the whole thing with zero gaps and, crucially, zero cutting?
All right, let's put some numbers on this to make it real. Let's say our floor is 24 units wide and 60 units long. I mean, sure, you could use tiny 1x1 tiles, right? Or maybe 2x2s. You could probably even get away with 4x4s, but that's not the question. The question is, what is the absolute biggest square tile you can find that will cover this entire space perfectly?
And the answer is 12, a perfect 12x12 tile. So why 12? Well, because 12 is the biggest number that divides both 24 and 60. It's their GCD. But look, the real question, the important one, is how in the world do you figure that out without just, trial and error? Well, that is where Euclid's genius really shines. So let's dive in and see how this thing actually works. There are a couple of ways to do it. We'll start with the original, super intuitive method, and then we'll check out the much, much faster version we use today. Okay, so Euclid's original idea, it was all about subtraction. It's super simple. You take your two numbers, 60 and 24, you just subtract the smaller one from the bigger one. So 60 minus 24, that leaves 36. Great. Now our two numbers are 36 and 24. So we do it again. 36 minus 24 is 12. Okay, now we have 24 and 12. Let's go one more time. 24 minus 12 is 12. And boom, the numbers are the same. As soon as they're equal, you're done. You found the GCD. It's almost like you're physically carving out these big squares from that rectangular floor we talked about.
You gotta admit, that subtraction method is pretty elegant, right? It makes total sense visually. But there's a catch. What if your numbers are, really far apart? Imagine trying to do this with 1,001. You'd be sitting there subtracting for, a very, very long time. Thankfully, there's a much better way, a shortcut. So the modern version, the one we use all the time now, it swaps out subtraction for division. Here's how it goes. You take the bigger number, you divide it by the smaller one, but you only care about one thing, the remainder. Then you just do it again. You take the smaller number and the remainder, and you repeat the process. You just keep doing that over and over until the remainder is 0. That's your signal to stop. Let's actually see how lightning fast this is. Let's take two kind of clunky numbers like 1071 and 462. Okay, step 1, divide 1071 by 462. The remainder is 147. Easy enough. Now we ditch the 1071 and just look at 462 and our remainder, 147. Divide those, the new remainder. It's 21, almost there. We do it one last time, 147 divided by 21, and what do you know, the remainder is 0. That's it, that's our stop sign. So what was that last remainder we got before we hit 0? It was 21, right? And that's it. That is our answer. The GCD of 1071 and 462 is 21. It's that simple. No guessing, no messing around, just a clean, powerful, and super fast process.
Okay, so it's a cool math trick for tiling floors. I get it. But why that epic nickname, the granddaddy of all algorithms? Well, because the simple, ancient idea has a kind of secret power. A power that literally shapes the world we live in today.
And hey, don't just take my word for it. The legendary computer scientist Donald Knuth. This guy is a giant in the field. He's the one who called it that. The granddaddy of all algorithms. And his reason was simple. It's the oldest, non-trivial algorithm that has survived and is still being used today.
Just let that sink in for a second. We're talking about an idea that's more than 2,300 years old. Euclid wrote it down in his book Elements way back around 300 BC, and honestly, it was probably kicking around even before he got to it.
And this is where it gets really wild. That ancient trick for figuring out the biggest tile for a floor, it's also one of the absolute cornerstones of your internet security. Yes, your internet security. No, seriously, its power is kind of staggering when you think about it. This algorithm is an absolutely essential part of the RSA encryption that protects you every time you buy something online or send a private message. But it doesn't stop there. It's used to reduce fractions to their simplest form. It's a key part of the error-correcting codes that make sure our computer data doesn't get corrupted. It even helps mathematicians prove some of the most fundamental truths about numbers. It is literally hiding everywhere, right in plain sight.
So let's just take a second to trace this incredible journey from an idea on an ancient Greek scroll all the way to the backbone of our digital world.
So yeah, it all starts with Euclid in ancient Greece. But what's really amazing is that the same basic idea popped up independently in India and China centuries later, where they were using it to solve problems in astronomy. Then you fast forward all the way to 1844, when a guy named Gabriel Lemay actually proved, mathematically, just how mind-blowingly efficient this algorithm is. And in doing so, he basically kicked off the entire field of computational complexity theory. And now, today, well, like we said, it's a cornerstone of modern cryptography.
Just think about that for a minute. A process, a simple idea that you can explain with floor tiles. An idea so simple, so elegant, and so perfect that it has stayed pretty much unchanged and totally essential for more than 2 millennia.
It really makes you wonder, right? What other ancient, brilliant ideas are hiding just beneath the surface, quietly powering the technology that you and I depend on every single day?